In this video, we want to look at creating custom validators with the Odin Inspector and optionally using the Project Validator. The validators can be used to check values of fields, whether the structure of a prefab is correct, if required components exist on an object, and so much more. Custom validators, when used in combination with the Project Validator, can become a powerful tool in the development of your project. This is especially true for larger teams where the programmers are not the designers. If you are unfamiliar with the Project Validator, it is a paid add-on to the Odin Inspector, and make sure to check out our earlier video covering the validator. But custom validators will work without the Project Validator. You just won't be able to scan scenes or the project automatically. There are two types of validators, attribute validators and value validators, and we're going to take a look at both by creating a few examples. It's worth noting that validators are highly project specific, and the validators that we'll create in this video are intended to show how to make validators and may not be directly useful in your project. We will, however, add a link to the validators created in this video and a link in the description below. A common mistake when creating an asset is to forget a required component on a prefab or other object in a scene. Forgetting a specific component may break the game, and in the case of tens or hundreds of prefabs, it's easy to miss a component on one, and it's tedious or even not practical to check each one individually. A solution is to make a custom attribute and custom attribute validator. This could be tailored to a specific type of component, such as a rigid body or a collider, or to make it more useful, we can make it generic to work with any type of component. To do this, we first need to create the attribute. It'll have one field to hold the type of the component that is required. The value of this field will then be assigned in a simple constructor, like so. Next, we need to create the validator class. This will inherit from attribute validator, which will take in two generic arguments. The first is the associated attribute, and the second is the value type that the attribute will decorate. Do note that we have added the namespace serenix.odininspector.editor.validation in order to access the attribute validator class. Inside the validator class, we need to override the validate function. We first check that the field is not null to avoid unwanted errors. Then it's just a matter of checking that the component exists on the game object. We can access the game object, or more generally, the value that the attribute is decorating with this.valueentry.smartValue. We can then call getComponent and give it the argument of this.attribute.type and compare the results to null. If the component cannot be found, then we'll want to display a message in the inspector. To do that, we first define the result type, and then we define the message that will be displayed. These messages will also show in the Project Validator if the object is scanned. The last step is to register the validator, and we do that with a one line at the top. Only the loaded assemblies have to be scanned for this attribute, and not every assembly, speeding up the scanning process and making it more efficient. With this done, we can do a quick test by adding our new attribute to a game object field, giving the attribute a component to search for, and then in the inspector, we can drop in a game object. If the game object doesn't have a component type on it, a message will be displayed. It's also worth noting that this attribute is similar to Unity's require component attribute, but the Unity version only works on classes and not on fields within classes. Let's take a look at a second example of an attribute validator that's a little more specific and a little less general to use. You can imagine a project where we want to ensure that sprites being used are of a specific resolution, and we could help remind ourselves or the designers with an attribute and an attribute validator. So once again, we'll create a new attribute, and this one will have an integer field that will store the desired size of the sprite. The size of the sprite can then be set by a constructor that takes in an integer. To make it a bit more user-friendly, we can add a second constructor that takes in a custom enum for the size of the sprite, like so. Then, just like in the first example, we need to create the attribute validator class while making sure to include the type sprite as the second generic argument. Once again, we need to override the validate function and check to make sure that the sprite field is not empty. We can then define two integers. One is the desired size of the sprite from the attribute, and the other is the width of the actual sprite that is in the inspector. If these two values are not equal, we can then display a message. In this case, a warning may be more appropriate than an error. In our message, we can also let the designer know the desired size and the size of the currently assigned sprite. Then once again, we need to register the validator, and we'll do that with a single line at the top. We can quickly test this by creating sprite fields, adding our new attribute, and assigning sprites in the inspector. If the values don't match, we'll get a message in the inspector letting us know what size was expected. So far, the two examples we've used are somewhat general, but validators can also be very specific and very detailed. Validators can also be applied to any value of a particular type throughout the project. For example, you might be making a game that has several plant prefabs that will be added to a list. Each of these prefabs may need to have several components on a child object in order to function properly. If every plant needs the same structure, we don't need to create an attribute and an attribute validator. we simply need to create a value validator. To do this, we create a plant validator class that inherits from value validator and takes in the type plant as a generic argument. Then once again, overriding the validate function, we check that the value of the field is not null before doing any further validation. In this case, we want to check that the plant has a child object and that the child has certain components on it. So we check if there is a child. If there is, then we get a reference to that child, and then we proceed to check for a collider, a rigid body, and finally whether the rigid body is set as is kinematic. Each of these conditions, if not met, has a custom message that is displayed in the inspector to help the designer ensure the prefab is correctly structured. To see this in action, we can create a list of plants, add a few prefabs to the list, and we'll get warnings on the objects that aren't set up correctly. Additionally, with the most recent version of Odin, since this is a value validator, the validation messages will show up on the root object, or in other words, on the object that has a plant class itself. This means if the plant object is a prefab, the scans of the project assets and prefabs will also identify this potential problem. Currently, any place that the plant property is shown in the inspector and the plant isn't properly set up, a warning will be displayed. In the case of the plant, we may not want this to happen, and we may only want it to show up on the plant class itself. To do this, we can override the canValidate function and return the value property.isTreeRoot. This will evaluate as true only if the plant property is the root object and not a child property of another property. This function creates a magic instance that is very performant and can check to see if the property could or should be validated before actually doing so. So there you go, 3 examples of how to create and use custom validators with Odin Inspector and optionally with the Project Validator. So I hope that was interesting and better yet, useful for you and your project. And until next time, happy game designing.